Hi friends, today I would like to present you my proof of Fermat The Last theorem. Everybody knows this theorem, so I don't lose time in explaining what is and the various conditions are necessary for the theorem. Of course, the theorem was already proven by Andrew Wiles, so the aim of this proof is give to everybody an accessible proof with simple instruments we will see are the sum operator used in a way you probably have never seen before. So what we can do now is represent power of integers as sum of integers using the telescopic sum rule. So we can write a to the n equal to the sum of x equal to 1 to a of x to the n minus x minus 1 to the n. So we can rewrite the Fermat last theorem with this left hand and in the right hand c to the n minus b to the n. So in case n is equal to 3, the right hand becomes c cube minus b cube equal to the sum of x equal to 1 to c of 3x squared minus 3x plus 1 minus the sum of x equal to 1 to b of 3x squared minus 3x plus 1. And remember the cutting rule, so how to remove a little sum from a bigger one having the same terms. It is equal to the sum of x equal to b plus 1 to c of 3x squared minus 3x plus 1. And on this one we can apply what is known the shift rules. Let this sum more similar to this one, and so we can rewrite c cube minus b cube as the sum of x equal to 1 to c minus b of 3 by x plus b squared minus 3 by x plus b plus 1. It will be useful to have always in mind this example doesn't work for a equal to 5, b equal to 6 and c equal to 7, and where you can see the first sum from 1 to 5 as for result 125, as we know, is the cube of 5, and in the right hand we have the sum of 3 by x plus b squared minus 3 by x plus b plus 1, that has only one term as the value of 127. So, of course, this is not necessary for mathematicians, but can be interesting for people who would like just to understand what happened here. Of course, one of the first case we have to prove is when n is equal to 2. But since it's the Pythagorean theorem, I will skip on it and I let it for another presentation where I will show that with my algebra this case has, of course, finite solution already known as Pythagorean triplets. So here the reason for representing the powers via sum and using x instead of I. You can see we can represent c equal to 7 in a Cartesian plane yx, and it is the sum of 1 plus 7 plus 19 plus 37 plus 61 plus 91 plus 127. And you can see you can square this column are called gnomons. I discovered it in the history of mathematics, and so the property of the telescopic sum is that you can square any variable or polynomials with these columns that has the property to square with his integer 8 exactly the parable between two integers, or we will see rational points. So this is c cube, this is b cube, so immediately we can cut b cube from c cube, having this one, of course, in the example a equal to 5, b equal to 6, and c equal to 7. And what we can do with the known rules is the shift, so we can put this column close to the 0. But these are all the things we can do with the known rules. Now we'll present you a new rule I have discovered studying sum, and will be very, very interesting. I discovered this 16 years ago when my son was born. I tried in any way to present this work to the math community, but no one accepted all these. The second very important point here is the key of the proof, is that we can now represent the sum via a sum of rationals. Means we can make an exchange of variable putting lowercase x equal to uppercase x over k. And in this way we can use not an index, but what I called a step is equal to the index by a scale factor we can choose when we make this change of variable, putting lowercase x equal to uppercase x over k. So taking n equal to 3 as example, but of course, as I've shown, this is just an example of the general rules for power I have already shown you. So what changes here is that we have a new lower limit becomes 1 over k, and then putting into the sum uppercase x equal to x by k, then we can simplify k where possible, having the sum from 1 to a, this is the classic sum, by the unitary factor is k cube by k cube, and we can now put it into the sum into these different ways. The factor here goes below every terms of the sum, and we multiply the upper limit is a by k. You stop the sum to a to the 6th, and if you divide all by k cube, of course divide a at the 6th by a cube. So again, a cube with a integers, it becomes the sum from 1 over k to a of 3x squared over k minus 3x over k squared plus 1 over k cube. All the proof turn on this property. I have called this the K invariance, means that I can put here any integer k, the result of the sum is always a cube. But what I will show is that when we make similar transformation on c cube minus b cube, we can again have it in function of k, but there is another trick. Will show you that he behave in another way, so it isn't a genuine cube. So let me summarize this new property for power. I call power of rationals now, and all is based remembering I present a power as a sum of these terms. I've called the Complicate modulus for powers, since it cut perfectly the nth power of any integers. So all is based on the exchange of scale. So I can write a to the n as the sum from x equal to 1 to a of m n, where n, of course, is the nth power we are choosing. So it is equal to the sum of lowercase x of 1 over k to a of m n k, where m n k is now the new telescopic sum for rationals. So the one allows me to move by a step is irrational from 1 over k to a. Of course, this one has to divide a, but I know that for any integers k divide a, so I can write here the general complicate rational modulus is n over 1. This is the binomial representation of x to the n minus 1 over k minus n over 2, etc., 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 till the constant term is plus or minus, depending on the n we choose, is 1 over k to the n. So you can see in the link at the end of this presentation to the My Volume 1, where I present all the details of this property, and also I will make another video where I focus just on the presentation of these properties. But since they are very simple, and this presentation is for mathematicians or students that already know sum and calculus, I will go on writing here the Fermat The Last theorem. The right hand, I remember we left as c cubed minus b cubed equal to the sum from x equal to 1 to c minus b of 3 by x plus b squared minus 3 by x plus b plus 1. It is equal to the sum from 1 over k to a of 3x squared over k minus 3x over k squared plus 1 over k cubed. You can put everything in an Excel table, and you can see what will happen here if you try to put on the equality. The left hand is a genuine cube, and the right hand it is not, using a step sum with k equal to 10. You see here you go exactly to 125, that is the cube, while in the right hand going ahead of step 01, 02, 03, etc., 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 we will arrive at 127, of course, as we know, but we also see that the result 125 for the equality is in the middle from these two values. And again, if you put k equal to 100, here we go exactly to 125 for a cube, and here we go more close than here to the 125, but we stop with 127 with 125 point. Some decimal here is bigger than our result, and we can go with k to infinite, and then just at infinite we arrive with here with an irrational x, little x, 225. This is not the point of the proof. This is just to show you how this algebra works, and then let one to think more easily using a table of numbers. On the Cartesian plane, we can represent c cubed minus b cubed as we did before, and we arrive to move the columns was here to here, and you can see in the example is a rectangle having base 0, 1 and 827, and now we choose a special k is equal to c minus b over a, and then this means we can cut in this case where a is 5 this column in 5 little columns having the same area is 127. This is the key of the proof. So now what we can do after this exchange of scale is giving what I've called the irrational first derivative is gq prime of x is these terms where you can see the c minus b over a factor. In the first term is power of 1, in the second term as the power of 2, and at the end as the power of 3, of course, by 1. And what we will do on that is again make another exchange of variable, because my intention is to put all this sum again between 0 and a, because it will be useful to talk and understand what will happen here. So I again keep one by one this little column, and I enlarge the base from 0 to 1 with another exchange of variable as again the same c minus b over a factor. These times enter into the sum close to the x-dependent terms only. So the new gq prime becomes an integer g prime of x, because moves of integer step again are 1, 2, 3, 4, and 5, and the sum is all this term. You can check also by making an Excel table as I did before. So the sum of all these terms is this one. Below this is the rational integer new derivative, and we will see going to the limit, making the limit of this sum, we can add a new continuous function is the new first derivative for c cube minus b cube is xi prime g prime of x. So let me remember what I did here with the scaling. The property of the K invariance is called scaling, and then I present the other exchange of variable. Let me stretch the limits of the sum are 1 over k and c minus b to the new limits are 1 and a, having the same c cube minus b cube result for the sum. So the first part is scaling, the second one is the stretching. So let me remember, we had c cube minus b cube equal to the sum having integer step from 1 to psi minus b. Then we make the exchange of variable and pass from uppercase x to lowercase x, having this sum now, and then again at the condition that c minus b is a factor of a, because we need to go to the upper limit for sure with a finite integer number of step. We can choose k equal to a factored by psi minus b, having c cube minus b cube equal to the sum from lowercase x of c minus b over a to c minus b of what I've called the new integer first derivative for c cube minus b cube is g prime I of x is equal to this term we already seen, and you can easily check. And so now another important point, how to pass from the sum to the integral via limits, and remembering from where we start, keeping as the upper limit the integer a. I've shown how to go rational with the exchange of variable we have already seen. Then it is simple to push this sum to the limit for k to infinite, having back the proof that 1 over k is 0, exactly equal to 0, but also the terms depending on 1 over k squared and 1 over k cube are exactly zero and not just negligible. So what is known as the transcendental law of homogeneity, we can prove it without any discussion on it, because we always use limits are 0 and a, so nothing has to change here. So terms are infimous of bigger order are not negligible but are exactly 0. So you can see the sum, we know, in the integer from 1 to a, then the sum into the rational, then we made the limit pushing k to infinite. The lower limit becomes 0 because 1 over infinite is of course 0, and here you can see these two terms are exactly 0, and so this k becomes what is known as the x. And so you can see here in the sum the gnomons becomes thinner and thinner. We can divide by 2, by 3, or by any k, and then when k goes to infinite we have exactly what is known as the integral. So this way to show the integral cannot be discussed by anyone. So in the 2017, if this approach was introduced by Fermat, no one can contest it. Of course, math is a nice discipline because sometimes something of very important is forgotten and discovered just 400 years later. So I let this simple proof for the readers of my volume 1. You can see it, you can find it in the link at the end of this video. I just remember that we can go rational just in case the curve we are representing is a parabol or a polynomial, because we can cut the gnomons and having again exactly the same squaring for the area is a. But we can also use any exchange of scale let us arrive to our upper limit. So, and this is quite strange for something, but is immediately be provable, that we can also use an irrational case is a third, for example, because in case we change our function and we use now 2x squared, and we make so a sort of summing in x, so we divide all by square root of 2, we can represent the square of 3 as the sum is going from 1 over square root of 2 to 3 over the square root of 2 of this new irrational modulus. So the sum that starts from 1 over square root of 2 to 5 over square root of 2 if you stop to 5, so we are representing the 5 square. So it is equal to this sum as 4 terms, 2x over square root of 2 minus 1 over 2. And you can check also in Excel that this works. So the condition is the step is to divide exactly the upper limit. So we must have an integer number of columns. So the index, rest, an integer. What change is that is multiplied by an irrational scale factors. So for our proof, being able to go into the limits, so to the integral, is useful to find what I've called g primes of x, because in this way we can easily prove if our rational transformation, so the two exchange of variable are correct, because if we push such sum to the limit, we have exactly to return to our initial value. And what is important here, and sometimes difficult for someone, is that when you write here letters, we are using real variables, so we cannot say anything about C when it's written here, not in a sum. So what I want to say now is that of course if we keep A and B integer by our choice and we left C to be a real number, of course the Fermat equality can be always satisfied by some real C. In fact, we can perform an integral from b is an integer plus 1 to k and push this sum to the limit, of course, and this becomes the integral between 0 and the real c minus b. So this is an irrational value of just this part, these terms of the sum, and we can see and easily check. Then we come back again solving these simple integrals with the known rules to c real cube minus b cube. This will be very different from the last trick I will do to prove Fermat the last you will see in a while. So once again, to be fully clear, we choose a and b integers, and we are not sure in case of Fermat equality if c is an integer or not. We are just sure if c is an irrational, there is for sure a solution. But all this is useful to transform our function is gq prime of x in g primes of x is a continuous function, is the sister of what is known as the first derivative for power of integers, so the function of the type n by x to the n minus 1. Now, since both g prime of x and f prime of x are between 0 and a, we can compare these two functions and prove our theorem. All will be very simple once we put on the Cartesian plane, and we remember that this area is c cube with a c let free to be a real. This is a cube, this is b cube, so the difference c cube minus b cube is this area, and it is clear with the integral, so leaving this one a real variable, we can squeeze this area below the first derivative from 0 to a. So there for sure exists a c real for what this area becomes equal to this one. We cannot do the same in case we are using sum, because below a linear derivative we have all triangles and we can do something. So, in fact, for n equal to 2, there are infinite many solutions, while for the curved first derivative, we have no more triangles, so we have just gnomons, but we will see it is impossible to move such gnomons from here to here without having back a rest if b and c are integers. So finally, we can always say that via integrals is always possible to solve the integral from 0 to I of g prime of x minus integral of 0 to a of f prime of x equal to 0. But Fermat asks if with a, b, c integers this is possible. So it is clear that if this is a continuous function and we can left c to be a real variable, we can adjust the height of this curve with c to be exactly equal to the area of a cube. So the area below g prime of x can be exactly equal to the area of f prime of x between the same limits are 0 and a. So what we can do now with this new toolbox? We will check if c cube minus b cube is the genuine cube of an integer a. But since its numerical value is unknown, then we take a look to it in his structure and its behavior. So to check if c cube minus b cube has the same structure and behavior of a genuine sum lead to a cube, so to a cube, we have to check if c cube minus b cube perform exactly as to a cube. So if and only if c cube minus b cube is equal to a cube, so it is a genuine cube, it is as a cube K invariant. So we can computate this sum changing K in a way is different from the one we see in the limit, and the result must be again a cube. So we can make a trick and show that when we multiply the sum represent c cube minus b cube by a cube over a cube, so a numerical one value, but we introduce this kind of multiplication into the sum, so presuming that the sum we are working on is exactly the sum lead to a cube, so we choose a multiplier k for the upper limit, so we multiply the upper limit by a, then more in general we multiply a by a at the m, and we divide all the terms but a to 3m. This must return exactly c cube minus b cube. Sorry, here is an error. This must be a at the m. So what happened is that doing that, changing m, we will see we have not back the same result, and this is why Fermat and Wiles are right, proving the effect of the multiplication by the cubic unit on a genuine cube left the results unchanged. So we can rewrite a cube as we have seen with our classic sum step 1, and then we multiply by what I called the cubic unit is a cube over a cube, of course by our sum. The result of this multiplication is of course the same, is a cube, but now we perform this trick. We left 1 over a cube outside from the sum, and we take into the sum a cube in this way. We multiply the upper limit by a, so this sum becomes a to the 6, and it is over a to the 3, so the result is unchanged. And then we take a cube into the sum, dividing all terms by a cube. So the result is again a cube. For those don't understand or don't believe, you just check it on Mathematica, and if you put here a square and you divide by a cube, the output is of course a cube again. So this will not happen on c cube minus b cube, as we will see in a while. Now the last step to prove Fermat The Last for n equal to 3, and then for all n. You remember we left our sum is c cube minus b cube with for sure c and b integer, because we write it via a sum. Is possible just if a, b and c are integers. Now we check if this new sum is k cubic invariant, so we do the same on a cube, so we multiply by a cube over a cube, and we introduce this unitary cubic factor into the sum. In this way we have the new upper limit is a by a, so taking by hypo that this is the sum that lead to a cube. If we multiply the upper limit by a we have to divide all terms by a cube, but this is an hypo. If the hypo is correct, then the result we have back must be again c cube minus b cube, but we have back another interesting object. Of course, this is not the final proof, because we here have letters, and so to have a proof here in the classic style, we need to prove that all positive and negative numbers here are not equal to 0. This is possible because this n is little and we know to solve a second degree equation, but this is not what I want to do. I have a more smart way to prove this, because I can now simply make this. I simply raise m, you remember, we can multiply here by a at the m and divide here by a at 3m, and so this is the first result we get before, and then we raise k to a squared, so we stop to a cube, so we divide by a to the 6, and what happened is that we have this part is k invariant, so rest the same, and here we have the last part of the sum is irrational, is k variant, and in fact we see that we have here a to the 4. The same if we multiply by a cube, so we stop to a to the 4, and we divide by a to the 9, and then here we have a to the 6. This means that this is not a genuine cube. So this sum cannot be a cube of the integer, because it not behaves like a cube, a genuine cubes. Of course, we push a to the limits. These terms here vanish, and again we have not again c cube minus b cube, because b is little than c, and then this term is for sure bigger than this, and so this is not exactly c cube minus b cube. So one more time, using Mathematica to prove I'm not cheating, we have a sum from 1 to a is for sure c cube minus b cube, and the develop of all these terms we can see here. The numerator are not a dependent, and at the denominator are all dependent by a at different powers. You can see here 3, here 2, and here a to the 1. And if we do the multiplication of the upper limit by a, or at the same we multiply by a square or a cube internal terms, and we divide all by a cube, we return back with a result that is no longer equal to c cube minus b cube. And we can prove this because changing the multiplicator factors, so putting here a square or here a cube, we get back different results. So this is not k invariant, so this is not the genuine power of an integer. And this proves Fermat for any n, because, as I've showed you, we can represent this term in a general way, so for any n. So once again, is it true just for n equal to 3? No. I hope it is clear my proof do not depend on the n you choose, since we can write g prime taking gq prime of x to the limits and having back what is the generic g prime x function of n and x. So you remember, as for what we did for the binomial theorem, as we did for m and a k, we can write gq prime of x as mnk of c at the n minus b to the n as n over 1 of c minus b over a by k, so we are free to change k and push it to the limit, by c minus b over a by x plus b at n minus 1, and the same for all the other terms belong the binomial develops. So we can use induction as we did to the binomial theorem to prove that this is true for n equal to 1, to 2, etc., to n, and also putting here n, the new n equal to n plus 1, we have back another genuine result. So in this way the proof is closed for any n. I show you the case n equal to 4 just to remember that using Wolfram, because Mathematica is not able to arrive to here, you can check. I don't cheat here, but this is really true. So we can express c to the 5 minus by to the 5 as the sum from x equal to 1 to 5 of all these terms you can see here. And then again, as we did before, this is k-dependent, and you can prove it because changing a to 8 square, we get back a result that in what you can see an invariant part is not dependent by the k we choose, because you can simplify a to the 4 here, etc., but no longer here and here and here. So we have the part that is k-independent and the part is divided by a to the 4 that is dependent but by the k factor we choose. So remember what we have to do when we have g prime of x and gq prime of x to prove that they are correctly written for any n. As shown, we have two ways. Proceed by induction exactly as we did for the binomial develop, as everyone can understand and prove, or find a more smart one-line proof I will show here after. So to understand that, you have to understood what my Complicate Modulus algebra say, so that we are using some as gears, so that such gears can be coupled one by one and works turning just in case they has the same terms or modulus or compatible limits, means you can make on it rational transformation to let remove the sum represent b at the n from the bigger sum represent c to the n. But if you understood what I said till now, you probably already imagine that we can represent a to the n in case n is an odd, because for even exponent is known a simple proof. So we need just to prove that in the case n is an odd or a prime, but for us odd is enough. We can write a to the n in this case as a by a at 2 by m. So this can be represented as a square, so using a linear derivative. And what we have to understood here is just that we have to find a way to put this multiplicator factor into the sum, and I hope it's very easy to be understood. We can do that because we are able to work with a third step, so we can choose 1 divided by square root of a as a step, so we can stop to the irrational is a to the m by square root of a, that is exactly a to the 2m plus 1 of the terms, is of course a linear terms. For irrational step is 2x divided by square root of 2 minus 1 to this squared, that is a. And we are sure this is for sure different from the same sum represent C at 2n plus 1, so with n odds, minus the sum represent b to the n with n odd, because we have no way to subtract this sum from this one, because we have different irrational factors here as no common factors, because remember Fermat's state, C, B and A do not have common factors. And of course you can see also the terms here are irrational and totally different. So this looks like a gears has different modulus, so cannot be coupled in any way. So there are no rational transformation to subtract this sum from this sum. So this is a very difficult point. I left it to you to think about that. My first part of the job is closed. I hope everyone knows what skull on the table does it means. Bye bye to everybody. You will find in the link at the end of this video the link to the PDF of this proof and to my volume 1, and also to the presentation of my Complicate Modulus Algebra. Will explain better all the first part here I give for simple and known. It was a long way for me to arrive here. Of course, all that can be shown on my 2 hand clocks.